Okay, so we are doing the Kinetics retake review, and Mary put a question on the Q&A prior to this, which is outstanding, and I was talking to Ms. Tillery, and we were thinking it'd be a great idea to actually put in our own questions, because she's doing some other stuff on Google Hangout. So I put in some other topics that if after I do Mary's question, if there's not another question up there, I'll do one of my own that I think some people would have, and also be able to review those things. So what I'm also doing at the moment is I'm opening up. I just put my kids to bed, so I apologize for not being totally prepared. But I did get some of this stuff out, and I'm putting bringing this stuff up so it's on my desktop so I can select it and show it to you guys. Okay, so there's one more thing I need to pull up, and then I'm going to start to take some, and I'll answer Mary's questions. All right. I apologize for a little bit of the lag. Okay, good. So let's look. Mary's question was, could you please review number 4 and number 12 on the new kinetics practice test, multiple choice and free response on the new kinetics multiple test? Oh, on the multiple choice. So number 4, number 12 on the multiple choice from the new kinetics, and the free response number 1D on the actual test. And I think that's all very plausible, all very reasonable. All right, so make sure I have my Bamboo pad open to be able to show you some of the answers. Thanks. Retake. Review. All right. The new review, or the new practice test. Where did I put that? There it is. Okay. So let me share this with you guys. There we go. And I'm going to make it a little bit bigger because I don't think that it's easy to see right now. Okay. And I believe she said number 4. Mary, I believe you said number 4, number 12. And I'm going to, I'm sorry, I suddenly lost the window. I opened up a new window and lost the original window. Where are you? There you are. Sorry. Number 4, number 12 on the new kinetics practice test. Okay. Number 4. Oh, good. Oh, perfect. This is what I was going to talk about too. Reaction mechanism. So you have these 3 steps to the reaction mechanism. And if you remember, we talked about the fact that the slow step is always the rate determining step. And so if you were to write a rate, you would probably involve these 2 reactants. Now, there's fast and fast equilibrium. Those are probably going to come into play. So if I just take a quick look around too, I see I start with Cl2, and then I make Cl. And then the Cl turns around and gets consumed. And then the Cl gets consumed again. So I would guess that, because if one of these Cls goes to step 2 and one Cl goes to step 3, if it's produced and turned around and consumed, it's an intermediate. So intermediates cannot appear in the rate law. So I know that when I make a rate law, I can't use the Cl. Looks like if I do, when you are doing an overall reaction, you cancel out the things that are on the same on both sides. Here we have another CCl3 that was produced and it was turned around and consumed. That's another intermediate. So it looks like the only things that are actual reactants and products, Cl2 is a reactant, CHCl3 is a reactant, and my products are HCl and CCl4. Remember that the slow step is our rate determining step, so that's going to give us our rate law. So let's read the question just to make sure that we're on the right track. Chlorine gas reacts with chloroform, the CHCl3, teal hydrogen chloride, and carbon tetrachloride. So there we have the hydrogen chloride, hydrochloric acid, and carbon tetrachloride. This decomposition is believed to occur according to the reaction mechanism above. The rate law that is consistent with this mechanism is given by which of the following? So we know that this is what our rate determining step would be. The Cl cannot be in there because it's an intermediate. So we have to have at least CHCl3. A, B, C, D all have that. And then we know that Cl cannot be in there, which eliminates number or letter A. So A is out because of the fact that Cl cannot be in there. So where's the strike through? Isn't there a strike through button? I thought I could strike through. Apparently, I can't do it when it is this large, but that's okay. You know what I am trying to do here. We'll just leave it as is. Okay, so A is out. That leaves us with B, C, and D. Now, it's 2 chlorines gives you the Cl2. So it's not just one Cl, so that's a problem. If it was just one Cl to Cl2, you could probably plug Cl2 right in there, but you can't. So which means that B would not be the right answer either. And because it's 2 Cls and you only have 1 Cl here, I don't know why in the world you would think you would get a superscript of 2, an order of 2. That is just not happening. So really, it boils down to being a half. If you kind of logically work through it, it has to have CHCl3, got it. Cannot have Cl, eliminates A. It's 2 Cls here, so you know that it's going to use, well, you know it's going to use Cl2 because that's the fast equilibrium. That's the one that provides the most, so it's the easiest to use. But you know that it can't be straight 1 to 1 because it goes from 1 to 2 on this side. So that means that B is out, and 2 being the superscript here would say that that's the order, or in some respects that would be the coefficient. Not the case here, so it can't be C. It's going to have to be D by process of elimination. There is some explanation here, and you can look at it. It's kind of following what we already said. You know, we're getting the overall, which we did that. You do a rate law like this, but the Cl doesn't appear in the overall reaction, so we can't use that. And the rate of this, so the K, let's say of this one, is Cl squared over Cl2, which is right here. And if you solve for the concentration of Cl, it's equal to the K prime, which is this original K, to the Cl2 to the half, okay? Because you divided, what you ended up doing is, you know, if you divide all of your superscripts, if you square root both sides or square root the whole thing, that's like saying that these powers are divided by 1. So that means the Cl is 1 from the Cl squared. It becomes Cl, and Cl2, the chlorine diatomic molecule, becomes a half. Now you can substitute that Cl half in there, okay? So that's why it's D. There's nothing this complicated on the test, but you should understand how that's arrived at, how that answer is arrived at, and that's how it's done. Okay, and we had number 12. Mary asked about 12. Here he goes. A reaction was observed for 200 seconds, and the concentration the reactant was monitored as a function of time. Which of the following best describes the order and half-life of the reaction? So, unfortunately, something happened when I zoomed in. Oh, shoot. I'm not sure how to move this over. Well, let's just say this. Like, I'm going to assume if this is 0, 50, 100, 150, 200, this over here is 0.02. Okay. So if we go from 0.02, to get a half-life, to get half of the quantity, you know, let me see if I can open this up. I'll bet that I can open it up in a way that'll be, because I don't think it'll make as much sense if I don't have it. Yeah, there we go. Okay. I'm going to switch the screen that I'm sharing with you guys. Let's see. There we go. I'm going to switch it to, no. Maybe this is it. There we go. Okay. So now you can see that it was 0 seconds, 50, 100, 150, 200. So if you're looking for the half-life, that's where your reaction right here is half of what the original was. Well, if it's 0.02, then half of the original would be 0.01, right? And 0.01 looks like it's pretty darn close to 200 seconds. Just shy of that, between 150 and 200, closer to 200. So if you're looking for the amount of time, okay, so half of that means about 200 seconds, which your only two choices are then B and E. Those are your only two choices. Everything else has got 100 around it. So then it's a matter of how quickly does it get there. And so another way of looking at it would be, well, you would hopefully extend it and say, okay, if 200 seconds is the half-life, in another 200 seconds, is it down to half of that? If it was 0.02 down to 0.01, then 0.005 would be what you're looking for, and then it would be first order. A first order reaction means that you're decreasing, and so initially there's a lot of decrease, and it slows down a little bit on that first order. A second order, there's an incredible amount of decrease. It goes down really quickly. If we look here, then I would say that it goes from 0.02 down to 0.015. So the reactant loses about 1/4 of it in the first 50 seconds. And then it loses, I guess I'm just eyeballing it, but it would be, so about 1/4 there. And then see how it kind of levels off at the 150, 200. It goes down real. So what's happening is it's not going down at an easier slope. It's going down at a really great slope. That means the actual slope is pretty darn steep. 0.02 to 0.015 to 0.012, and you can see that from there it just levels off pretty quickly. So that is actually, if you're looking at it, first order would be, then half of at 400 seconds, half of that would be remaining. But you can see by the slope is changing from the 100 to the 200, that slope is leveling out quite dramatically as well, which means that it was steep at the beginning, very steep at the beginning, and not so steep at the end, which means it's not going to keep going in that regard. So I'm going to guess it's that second order. However, and you're not going to do this on the multiple choice, it's a little bit easier on the multiple choice on the test. They have you graphing it out based upon, you plug in the numbers and make a graph, and you see which one gives you a straight line, and that's your answer. On the test, a half-life, and if you remember from the actual unit test, you didn't have to do that. On the actual test, it was a matter of saying, okay, if I start with 0.02, then I went down to 0.01, and then I went down to 0.005, and then I went down to 0.0025. So it's very similar to the way you do nuclear chem half-life. So they're not going to be this difficult, but I like it because it's making you think about the relationship between first and second order half-lives. Okay, so that's number 4 and number 12, and now we have number 1D on the actual test. So, okay, 1D in the free response. So I will share that one now with you. Okay, and I'll make this a little bit bigger so that you can see. Okay. So here's number 1, and we go down to D. So this one was saying in another trial, the student mixed the 0.10 molar sodium thiosulfate, with hydrochloric acid. Calculate the amount of time it would take for the concentration of the thiosulfate ion to drop to 0.02 molar. And so we use the rate laws only with initial concentrations. Anything that happens later on in the reaction, we use the integrated rate law. Now, you've already established from B that it's a first order. So you know you're using this natural log of A at time t is equal to negative kt plus natural log of A at time 0. Since you are trying to find t, you are isolating t by itself. So that's why the natural log of A at the initial concentration or initial time is then subtracted from both sides. So it's natural log of A at time t minus natural log of A at time 0. And you're going to divide that whole thing by negative k to give you t. And you solve for k in C. So then you just plug it in. Of course, the key to this whole thing is that you had to get the rest of it correct. 1D won't make sense if you don't have B and C done correctly. So if you did B and you got it first order, you know you're using the natural log. And just as a reminder, that natural log of, actually what I should do is I should take this. I think this equation is on your equation sheet. So that's the original equation. And then you're isolating it for time t. So you're subtracting natural log of A times 0 from both sides, dividing both sides by negative k, which is the 0.04. And then, of course, this should say seconds because the time is 4.02 seconds. But I didn't make that required. I let you guys go on that, which is fine because you had to have the units and the one above it. So hopefully that makes sense. If it doesn't, of course, you should come back and refine your question a little bit. But that was those questions. Number 4, number 12 on the new Kinetics practice test, and number 1D on the actual test. All right. So looks like there's some other questions. Good deal. Number 1B on the actual test. So this is ARIA. We're going to do number 1B, and this is good because we're still on the test. So 1B. All right. Now the deal here is that I told you guys you're going to have to learn how to do this with math. Okay. And so that's what we did. Just by your answer with calculations. You have to compare the two rates to each other with putting the biggest rate on top. So you can see this answer right here. All right, but I'm going to show you how you can do it with different rates and still get the same thing. Okay, so you got that. It's on the screen. I'm going to switch to my Bamboo tablet. Okay, and there we go. Okay. So I believe it was trial 2 and trial 1, and we're going to do trial 4 and trial 5. So this is number, I don't want to do red. All right, number 1B. So we're going to compare trial 4 and 5. Okay, and with 4 and 5, your rate law that you already wrote, because you're looking at it and you noticed, or actually, well, you're trying to figure it out, but you only have, let's see, they don't tell you what the order is, but the only thing that you're dealing with is the S2O3. So rate is equal to K times the concentration of S2O3 2 minus. Okay. So the rate is equal to the rate of disappearance. The rate of appearance is equal to the rate of disappearance. So that's what we're talking about there. And which means that we put the rate of the bigger one. So if we're comparing 4 and 5, the larger rate was actually number 5. So the rate of 5 divided by the rate of 4, so equal to K times the concentration at 5, which was 0.125, divided by K, and the concentration at 4 was 0.112. Okay, let me write that out one more time, and I'm going to use the actual rates this time. So 0.051 divided by 0.045 is equal to K times 0.125 divided by K, which is 0.0, nope, I did it wrong again, 112. 112. Okay, so in the K's, oh, by the way, in the order we're going to put up here, I'm just going to make it an A. The order is, we don't know what the order is, that's what we're trying to calculate. The K's will be the same. The only way K is different is if you have a different temperature. And those are all the same temperature, so K's go away. So pull up my handy dandy calculator. I do 0.051 divided by 0.045, and this number ends up being 1.133, etc. is equal to, and by the way, this is the same thing as saying 0.125 divided by 0.112, all of that to the 8th power. So when I do that, 0.125 divided by 0.112, I end up with 0.116 to the 8th power. Okay. Oh, excuse me, I need a little water. So this A has to be equal to 0, 1, or 2. Okay. If this A was a 0, then that would be equal to 1. If that A was a 2, that would be, let's see, 0.116 squared is equal to, if it was 2, then this would have to be 0.0134. And that's not what's happening. Oops. Sorry. I wrote this incorrectly. Let me fix that. 1.16. I'm sorry, 1. Jeez, I really wrote that wrong. 1.116, sorry. Okay, there it is. So these are really close together. So that's going to have to be a 1. So A is equal to 1. So it's a first order. Okay, you have to be able to do that calculation. You have to. That comes up on the test, the AP exam. You are also going to have to do it again on the retake test. So be familiar with that. So that was a good choice there, Aria. So that's that. That's how you solve for 1B. Okay. So we're done with that question. Let's go on to Joanne's question. Could you review test question multiple choice 8 and 10, also for response 1C and 2C? I'm going to assume you mean let me just double check to make sure. Well, I'm going to go ahead and do the unit test. I'm going to do the unit test. And Joanne, if you actually meant the most recent practice test, I'll need you to repost that question. Okay, so review test question, multiple choice, unit test, multiple choice 8 and 10. Okay, so let's share that test with you again. Okay, so 8. When the concentration of substance B in that equation above is doubled, all of the factors being held constant, is found that the rate of the reaction remains unchanged. So we do B, so here's our reaction. We change B and nothing happens to the rate. Well, if nothing happens to the rate, if you were saying that this is part of the order, that B would have to be 0 order, right? So just on the first guess, I would say, okay, B is probably going to be 0 order, but we'll look for it. The most probable explanation for this observation is A, the order of the reaction with respect to substance B is 1. Well, definitely not. B, substance B is not involved in any of the steps in the mechanism of the reaction. I don't know, we'll see. Substance B is not involved in the rate determining step of the mechanism, but is involved in subsequent steps. Now that's interesting. Rate determining step. And substance B is probably a catalyst, and as such, its effect on the rate of the reaction does not depend on its concentration. Now that's kind of interesting too. So let's look at D because we just read that one. Substance B is a catalyst. Now, if this right here, if up here, this is the overall, if that's the overall rate of the reaction, not just the first step, if that's the overall rate, and they didn't give us anything else, we're going to assume it's the overall, because they wouldn't, I mean, taking just one thing out, I don't know, maybe not. But if this is the overall, then B would not be right there, because it wouldn't be in the overall, it wouldn't be, if it was a catalyst, it wouldn't be in that, I'm sorry, it would, if it was a catalyst, that would not appear in the overall reaction because it would cancel out. It would be at the beginning and be at the end, but not. So I'm going to say no to D because that's an overall reaction and B's there, so it can't be an intermediate, nor can it be a catalyst. Then the next question says, or the next choice would be, let's say B, that was the one I said, maybe substance B is not involved in any of the steps in the mechanism of the reaction. Now that's interesting. None of the steps have B. Well, if none of the steps have B, why is it here? It would have to be if it's in some of the steps. So B just is not true. That leaves us with C. Substance B is not involved in the rate determining step. So if this is the overall, okay, so B appears in the overall of the reaction, but the rate determining step is what tells you what determines the reaction. If you have a rate determining step, then the pieces in the puzzle, the pieces, the elements, the compounds in that reaction must have some effect on the rate. So that means that makes sense that it wouldn't be a part of the rate determining step, but is involved in subsequent steps. Totally makes sense because B has to be somewhere in it because it's a part of the overall reaction. It doesn't affect the rate, which means it's a 0 order, which means it's somewhere in there, just not the rate determining step. So that's why C is the right answer. And 10, the proposed step for a catalyzed reaction between Ce4 plus and thallium plus are represented by the products of the overall catalyzed reaction are. So this is where you need to go through and cancel out the same species on both sides. You're adding them all up as you would in Hess's law, and you're finding which ones actually come through as part of the overall reaction. So we look at Ce4 plus. Ce4 plus is there at the beginning. There's nothing on the right side, so I know that one's going to be there. This Ce4 plus, yes, that would be, these are both it's a reactant. You'll end up with like a 2 Ce4 plus. There's no Ce4 plus, so that's definitely true. The Mn4 plus is right here, but it cancels out with this Mn4 plus. So I know that Mn4 plus is not a product, which means that C cannot be the right answer. Then I look at Mn2 plus. Mn2 plus is on the left, and Mn2 plus is on the right. Mn2 plus cannot be a product. That means C and D are out. I look at Mn3 plus. It's on the react side and the product side. So that's going to cancel out. So that means B, C, and D can't help. Now, by process of elimination, it's A. But just to confirm, we look here that Ce3 plus is a product. It's not a reactant. And Tl3 plus is a product, and it's not on the reactant side, so it's not going to cancel out. So it means that Ce3 plus and Tl3 plus, both are products that they are not present on the reactant side, so they stay as products. So that means that they're in the overall reaction. That's why A would be the correct answer for multiple choice number 10. Okay, so let's slide on down here to free response 1C. This one, I feel like we kind of started the answer. If you know how we got the rate law, right? The rate is equal to the K times the concentration of our lone reactant to its power. And with calculations, we determine it to be first power. So that means that it's K times the concentration of your reactant to the first power. So now it's saying, okay, so at the initial, you can plug in all the initial numbers, and we want you to find the rate constant K for the reaction. And when you have that reaction and you plug in those numbers from any one of the trials, you should get the same K. In this case, it was 0.40 seconds, inverse seconds. So what I'm going to do is I'm going to do that again on the bamboo paper. I'm going to show you how to walk through that and get the value for K with its units using a different trial. Okay, so let's use trial 5. So I'm going to share the bamboo paper and do trial 5 and get the K. All right. All right, oops. Okay, let me go to a different page as well. All right, so this is number 1C. Okay, so we're going to use trial 5, and we have the rate at 5 is equal to K times the concentration of the thiosulfate, I should do that, the thiosulfate ion at 5. And it's to the first power. And so this is the, I'm just going to put a 5 here to note that's the concentration at 5. So the rate at 5 is 0.051. And the rate and the units based upon your table are molarity per second. And that's equal to K times the concentration, which in this case would be 0.125, and concentration of units of molarity. Okay, now we're solving for K. K is equal to, we have to divide both sides by 0.125 molarity, divided by 0.125 molarity. So let's scoot down a little bit. If we're solving for K, K, and these cancel out, is equal to 0.051 molarity per second divided by 0.125 molarity, which means that these molarities get canceled out, leaving you with the inverse seconds. And if I plug in 0.051 divided by 0.125, I get as an answer K is equal to 0.408 inverse seconds, or 1/seconds. Now there's only 2 sig figs here, so that 8 would go away, leaving me with 0.41 inverse seconds. So that's what K is equal to based upon the data from trial 5. Okay, so if you had put 0.41, I absolutely would have given you those points. So hopefully that makes sense. Again, you have to be able to do that for the retake on Friday. It's going to happen just like that again. Good question. You guys are asking really good questions. I like this. Okay, so let's go to, Aria has a question on multiple choice number 6. Again, I'm assuming this is the unit test. So I'm going to share that test again. We'll look at multiple choice number 6. Okay. The oxidation of iodide ions by arsenic in acidic aqueous solution occurs according to the stoichiometry shown above. The experimental rate law of the reaction is rate equals K times arsenic acid times iodide ion plus, or times the hydrogen ion, hydronium. Now, you don't even need this whole reaction. All you really need is the rate law, because what they want to know is what is the order of the reaction with respect to I minus. Well, all you're looking for is what's the superscript after the I minus. If there's nothing there, it's assumed to be 1, which means that the correct answer is A. If there had been a 2 there, it would have been B. If there had been a 3 there, C. A 5 there would have been D, but it was just nothing there, which means it's a 1. So that's why number 6 is A. Okay. Aria again. Could you do number 9 on the retake practice test? Absolutely. So, where's my practice test? I am assuming this is the new on the retake. Yeah, you already said. You said. I'm not assuming. You told me. This is the new practice test, number 9. So let me find it. I think I've got it hidden. Feels like oh, there it is. Okay. Sorry. You said number 9. Okay. Let me make this a little bit bigger. I think you guys probably have a hard time seeing. Okay. So let's see. Okay, the energy diagram for the x plus y equilibrium with z is shown above. Great. It's right there. The addition of a catalyst to this reaction would not cause a change in which of the indicated energy differences. So the addition of a catalyst, okay? What does a catalyst do? That's our first question. What does a catalyst do? A catalyst lowers the activation energy by providing an alternate pathway, okay? Lowers the activation energy by providing an alternate pathway. What that would do is that would give you a lower crest, a lower hill on this right here. So, and actually, I want to draw this again because this ties in. Well, you know what? I'll answer this and I'll get to it later. If it's going to lower this right here, that means that it's going to affect I right here. That's number 1. That is, of course, the activation energy, the amount of energy it takes to get up and over it into your reaction. So it's going to affect 1. And according to this graph, it affects 2, right? Because it's going to lower that line right there. So it takes, and the 2 is like the overall amount of energy from the peak down to the bottom. 3 is the actual, like, we'll call it the delta H, which is a state value, a state function. It doesn't matter what the pathway is, just what is the difference in energy between the reactants and the products. So 3 doesn't change because you don't change that because, again, it doesn't matter pathway. Catalyzed, uncatalyzed, 3 will stay the same always. It affects 1 and 2. And let's see. Oh, I'm sorry. The addition of a catalyst to this reaction would not cause a change in which of the indicated energy differences. I didn't read the whole question. So 3 is the only choice because that's the only one where would not cause a change in which. It wouldn't cause a change in 3, which means that your answer should be C for that one. Okay. So later on, I mean, depending on if there's time, I'll go back. I want to show you that graph again and talk about the positions on the graph. Good. Okay. So at this very moment, there aren't any other questions. So I'm going to continue with Aria's, his lead-in question, and I'm going to continue talking about an energy diagram. And now I'm going to draw it on my bamboo paper. I'll go to another page. Okay. And we're going to make it lots of colors because colors are fun. Okay, so this is the energy diagram. All right. So we go down here, we go across here. Okay, this over here is potential energy, P, potential energy. Along the bottom, you have the reaction coordinates. Okay. And we're going to make a graph. We're going to make it in blue because I like blue. And a lot of them do this little thing right here. Okay. And we're going to make our actual reaction right here. So we've got A plus B goes to C. Okay, so this is our initial. That's our initial. Okay. And then when it gets up to the top, you have a ... it's kind of bonded a little bit with B ... to C. And this, of course, I'm going to put these in orange. Or purple. I'm having so much fun with colors. This is your transition state. Okay. It's also known as your activated complex. Okay, so you're cruising through this, and then when you get down to the other end, you're going to have an A ends up with BC, something like that. I mean, I'm not real good with that, but you get the general idea. Whatever I'm trying to say. The idea is that the B is shifting from the A to the C. It's not a very good reaction, actually, because there's not the same letters on both sides, but what I'm trying to do is give you more of an overall. Should have picked a better example. My apologies. Now, we're going to say that orange here is, so there's this level right here. Okay, so that's our initial one. Now, up here at the top, that's the peak. So this large one, pretty big, this is your activation energy, and it's uncatalyzed. Okay. Now, if you had a catalyst, it's going to do this right here. Okay, and then it's going to join it again. Now, this right here is the new E of A, and this is the catalyzed one. Okay, so that means that if you add a catalyst, I'm going to put it black. So, catalyst lowers the activation energy by providing alternate pathway, which also means that the potential energy, we'll call it, of the activated complex has been lowered. Okay, so I wanted to emphasize that point so you could, I don't know, think about that. Okay, so that's what I want to talk about with the energy diagram. And I see that Joanne's put another question, so let's take a look at that one. The actual test, free response 2C, so I'm going to share that document with you. Actual test. Oh, I didn't open it up. Okay, hold on a second. Minimize it in my window. Okay. Now I forgot the question. We're doing 2C. 2C. Oh, there we go. Okay. So that one is the presence of metallic nickel causes an increase in reaction rate. So anytime you have a metal that is not very reactive, so platinum, gold, silver, nickel, it's kind of, I mean, it's not very reactive. It's not as inert, let's say, as platinum, but they're often used as catalysts. So if in the question it says you add this piece of whatever it is, and it's not a part of the original reaction. So you look up here. Here's the reaction. Okay, adding metallic nickel is not a concentration increase. If you increase concentration, that speeds up reaction, right? But if you add something totally different and it speeds up the reaction rate, you just added a catalyst. Okay, so you're trying to describe why it increased its reaction rate. So okay, well, nickel is a catalyst, and you would say that lowers the activation energy needed for the reaction. So if you lower the activation energy, more molecules have the needed energy when they collide. so the reaction rate increases. This is, of course, yet another graph that we need to take a look at. And there we go. So in this graph, there we go. I'm sorry, just give me one moment. You don't see, oh, I didn't bring it. I apologize for slowing this down. Okay. So we have the number of particles on one axis. Hold on one second. It's called a Maxwell-Boltzmann distribution because you can use it for a lot of different. You can use it for a lot of different. What am I trying to say? You can use it for a lot of different energy type discussions. I wrote that on the wrong axis. Sorry. Number of particles. Sorry. So this is number of particles. This is energy. Okay. Maxwell-Boltzmann. Okay. So here's what we would say. So you have this. You're talking about the number of particles in a sample that have a given amount of energy. So it's usually like this. They've got low energy at one end, and then the energy increases, the number of particles that have that energy increase, and then it kind of tailors off that end, okay? And for a reaction to happen, a lot of times, that is up here. Let's do it like this. Let's make it green. It might be up here. So that's the energy. That's the number of particles, right? That area under that curve right there. That's the number of particles that have the energy. And we would call this the activation energy. And so that's the number of particles that have the energy needed to make the reaction happen. Well, what happens when you add a catalyst? Okay. That, of course, lowers the activation energy. And so let's say suddenly you're down here. Okay, you've lowered the activation energy. So now all of these molecules have the necessary energy because you've lowered the amount of energy needed to make that happen. Okay, so you've moved that. Now, for fun, we're gonna make another one of these. I should have made this smaller. That's okay though. We're gonna make it, oops. No, I didn't want that to be. Okay. Let's make a smaller one. And we do this graph again. Okay, make this bigger. All right, so this is energy. This is number of particles. Okay, and using the green, this is your EA. What happens if you increase the temperature? If you increase the temperature, the number of particles that have a given set of energy increases. So now your curve is no longer like that. Your curve is like this. So it's still the same shape, but oh my goodness, look at this. Okay. So this would be considered, from here to here. Let's make that blue. So from, sorry, trying to be clever. So from here to here is a change in temperature that increased. But look at the number of particles. Originally, there was only this many particles. And now, oh my goodness, look at the number of particles that can now do this reaction. Okay, small increase in temperature, huge jump in the number of particles that can now react. So you've got so many more reactions are happening because of that. Okay, that was one of the questions on there. So just kind of make you aware of that. Okay, then let's see what else. Oh, those are the two biggest things I want to talk about in regards to those. Those are Maxwell-Boltzmann distributions. Let me see if I can write that down one more time. Maxwell-Boltzmann. It was in your notes, but I don't think we really talked about it. Boltzmann distribution. Okay. Okay. Going back, see if there's any other questions. Nobody had another question, so let's take a look at, my review topic 3. I said we're going to talk about rate laws, calculation for order, rate constant, initial rate, and using integrated rate law. As it turned out, we already did that, so if you have that question, if you jumped here, you need to jump back. And it's anything that relates to 1B, C, or D. 1B, C, or D. On the unit test, we covered this. And that's what I wanted to do. So that was good. And then finally, the reaction mechanism, we actually did cover. That one was, forgetting right offhand. Reaction mechanism was, number 10 on the multiple choice. I want to talk about that. And then I think on the other practice test, we talked about it in number 4, which was good. So those are the two, I believe, that, and that way we covered it. Yes, those were the two. Okay. So I feel like I covered all the things that I wanted to cover, that I thought you needed to. You had a chance to ask some questions. Are there any other questions? I'm not seeing anything pop up. It's 8:55, so we've been going for about an hour. Of course, there's tomorrow, so people may be watching this video tomorrow night, but those of you that watched it tonight or participated tonight, if there's some detail or something you're doing and you're having questions about, please come in and see me tomorrow. Tomorrow is +3. I have a lot of students that are doing makeups for the test, and they're doing essential skill correctives. So plus period might be really stacked. I think lunchtime will be a better time if you have questions. So either before school, lunchtime, right after school, I have to go to conditioning for soccer. So I'm not going to be there for very long after school. And then, of course, Friday is the retake. So my recommendation is tomorrow morning before school or at lunch. And then tomorrow night I have a Google Hangout for General Chem, because they have a retake on Friday as well for their test. So I'll be doing that. So it might not be easy for me to answer questions or answer emails. No more questions appeared, so I think we are good. So good luck. Get some sleep tonight. I know you guys will do fine on this test. And make sure you ask me any questions if you have them. All right. Thanks a lot, everybody. Goodbye.